Um, yeah, so I just want to begin with a motivating example, and it's great that the last talk was talking so much about education because that's the motivating example that I'm going to discuss. So we can imagine a teacher and an elementary school student who is learning the similarities and differences between fruits and vegetables. And so in this educational setting, we might present our student with a fruit like an apple and ask them to categorize it as being either a fruit or a vegetable, and the student might categorize that one correctly. And then we continue this on with pineapples, carrots, oranges, and other examples. But eventually the student might get some categorization incorrect, such as the tomato, which students often say are vegetables, even though they're botanically fruits. And so the question is, what's going on in our student Jamie's conceptualization of fruits and vegetables that cause them to incorrectly categorize this one? And so in the real world, we might ask the student why they got this categorization incorrect. And they may say something like tomatoes go in salads, so they're vegetables. And so this incorrect understanding of something that defines fruits versus vegetables allows us to provide feedback to the student, like saying not all salad ingredients are vegetables. And it also allows us to determine the next best example for the purposes of educating this student, like showing them the olive, which also goes in salads but are fruits. And because that makes sense to them, the student is appropriately learning from this. And so we can think about what's going on in the brain of our student by sort of plotting this psychological space of vegetableness and fruitness that this student has that they're using to categorize fruits versus vegetables. And since they got these ones correct, we can think of these as being high confidence fruits and high confidence vegetables. And then there's this area that the student is not really sure whether it is a fruit or vegetable because they have a low rating for both. And so thinking about this more abstractly, we can see where this student's categorization boundary is coming from. They are basically saying that anything above a certain amount of fruitness in their mind is going to be categorized as a fruit, and similarly with vegetables. And that's the reason that they're incorrectly categorizing the olive and the tomato as being vegetables. You can see that here. So these two are incorrect. And so one way to try to understand where these judgments of how vegetable and how fruit a stimuli are might be to form some encoding of these concepts. So if we had a encoder that could form some representation of fruits and vegetables, then essentially the task would be to form those representations and then compare the similarity between these encodings and some average of both of the categories that we're interested in. So if we want to know how similar broccoli is to a vegetable, we can compare the similarity between its encoding and a vegetable, the average vegetable encoding, and the same for fruits. And so in general, we might want to be able to do this with any form of stimuli, not just fruits and vegetables, as well as any number of categories that we're applying this to. And thinking back to that psychological space, here we can plot the similarity of this abstract concept that we're thinking of and the similarity it has to the two categories that we're interested in, and do that for some range of stimuli and then form some categorization boundary. And the key point is that this is supposed to be describing one individual student's conceptualization of these categories, and the use case of it is in understanding their incorrect and correct categorization. And we can see here in red line, this is what would be a correct categorization based on the similarities that this student is displaying with their behavior. And the goal of the feedback that we provide to the student is to fix this incorrect categorization so that we can get them to properly identify these two stimuli as being part of category 1 in this case. Additionally, we can try to strengthen that correct categorization by giving them the next best example to clarify the point that we're making in our feedback. And so those are the two applications for trying to predict an individual student's categorization in this embedding space. The first is providing individualized and contextual natural language feedback for education and training. And the second application is in selecting the next best example to show them based on their individual experience. And so the example of fruits and vegetables is a little bit simplistic. And so instead, we're interested in more complex stimuli. And here, the use case that we have in the paper is in students categorizing emails as either being phishing, which are dangerous emails that are trying to steal your information, or ham, which we call safe emails that are not phishing. In the study that we performed with human participants, we also were interested in how well GPT might be able to write phishing emails. So we had different conditions where GPT was writing the email versus a human cybersecurity expert. And we also varied whether the presentation of the email was just plain text and compared it to a version where GPT was writing HTML and CSS code to stylize the email to see if it would be more difficult. And so this is what the platform looked like. We had the email on the left being presented to them. The participant categorized it and showed their confidence in the action that they would take after receiving it. And on the right, they received feedback from a large language model that they could also converse with. And so what we're plotting here is one individual participant's sort of their representation of the level that each of the emails that they categorized is ham, so that's the safe emails, versus being phishing. And the colored background is trying to display their categorization boundary. And these are only the emails shown to one individual participant who was observing GPT-4 written and stylized emails. And the way that we get these sort of human like subjective similarity measures is by combining together their reaction time, their categorization, and their confidence to get at this sort of metric of the degree to which the participant believes that something is a phishing email versus a ham email. And just to show you how different participants' categorization boundaries can be, this is showing two different participants who are both viewing GPT-4 written emails. And then this is another one who is viewing human written emails. And then on this slide, we have an average over all of the emails in the data set across all the different participants that we gathered annotations for. And so one easy way that you might form these measures of how people are judging similarity between emails and the categories we assign to them might be to use a large language-based method where we put in as input the language, the textual information contained in the email. We form some embedding of it, and then we get some similarity score based on the cosine similarity between the email embedding and the average of the categories, both of the categories that we have, the phishing and the ham emails. And so if we were to do that and then compare it to our individual subjective human measure, here we can see in the top right, this is the in light blue phishing cosine email similarity, and then in light orange, this is the ham emails. So one clear thing is that both of the types of emails are being measured as being much more similar to each other compared to the human sort of subjective similarity measure that we are defining. And so there are a lot of approaches that exist to try to get these cosine similarity metrics to be more similar to observations from human behavior. And one of them is to weight the embeddings. So here the embeddings are of size 3000, and this weighted cosine similarity metric approach basically forms for each of the participants a matrix that is optimized to approximate their individual similarity that they are judging for each of the emails. And here we're plotting that to show that it is still a little bit different from the humans, but obviously a lot better compared to the unweighted version of cosine similarity. There's also methods like pruning where we might, it's a similar approach to weighted cosine similarity, but the weighting matrix M is now very sparse, so a lot of the values are 0, and so we're really just selecting a subset of the embedding values to use for comparing similarity. Another method might be to use semantic categories of the emails. So here in the data set that we had, there were 6 categorizations that were annotated by human cybersecurity experts, and those were used to judge the similarity. Here, it was very poor and not very closely related to the human one. What you would likely do in the real world is to include more categories and more semantic information. But because we didn't have additional categories already annotated, we just used the ones that we already had for this data set. And then finally, the last method used for comparison is just an ensemble of all the different previous approaches where we weight them again for each individual participant and then average them over the entire data set. And so all these different existing methods for comparing the similarity that a human might form for the stimuli that they observe and the categories that they are trying to assign onto those stimuli is that they all are really supposed to be designed for use in very large data sets and reflecting the average human across the entire data set. And they're not really applied onto necessarily getting a individual's metric of similarity that they're using. And this is a big problem for learning settings, because if we just conceptualize the similarities and differences between how humans are categorizing these stimuli, then we might not give them feedback that is necessarily in relation to what's going on in their head as they're trying to categorize these. Additionally, they are not cognitively grounded, and what I mean by that is they're not directly connected to the learning that takes place in individuals as they're categorizing different stimuli and getting feedback from them, as well as constraints such as memory constraints, which is problematic. And so the approach that we describe in the paper is to use an instance-based learning model. I'm not going to go into a ton of detail about IBL models. You can think of them conceptually as being similar to reinforcement learning models, but instead of learning a policy to predict the optimal action to select in a task, we keep a memory of all the experiences that an individual student or agent has had in that task, and then we predict their behavior through a series of equations that are supposed to be describing the cognitive mechanisms that humans use, such as recognition, judgment, and choice selection. And so in the specific case of the email task, we first, again, form those embeddings from the large language model, and we use those as input to this instance-based learning model, meaning that the memory of this model is all of the embedding email embeddings that one individual participant has seen. And so after this, the way that we actually go about calculating how an individual person would measure the similarity between different emails or the level of phishing and ham of an individual email is to first predict the value that that individual would assign onto each of the categories. So here it's phishing and ham. And then we basically do a softmax over the different categories. And that gives us a metric of similarity that's highly close to what we observe from human behavior. And here we, again, are still averaging over the entire data set, but you can see from this that it's much closer to the measurements compared to the alternatives that I showed previously. And also this same thing is observed when we look at individual participants. So here on the left, this is comparing that prune similarity metric with one individual participant, the ensemble, and then finally our method of using this instance-based learning model to predict similarity. We also have in the paper some additional, display of results. This here is just showing 3 random participants, but we also showed when we average over all the participants, they still had the highest accuracy or similarity between these distributions, which is this KDE score shown in the bottom right. And this is also true when averaging over all participants. And we can also predict individuals' decision making by iteratively updating these distributions and then using this logistic regression classifier to predict how they would categorize the next email after it's being shown to them. And so that's the regression accuracy that's shown in the far right. And then finally, we did perform a follow-up experiment where we gave natural language feedback that was either informed just by a large language model alone, which is on the right here, or the method that was using this IBIS approach of predicting how people are using Similarity, and that's in this both column here. And here we're plotting the improvement in categorization accuracy from the training. And so just to show that the optimal was shown when we are selecting emails for educational purposes and providing feedback with the method that we propose. And that's everything I had.